want to try to keep my momentum going. So my aim is now to do maybe 2 more problems, but the precise number will depend how they go. Sometimes I get stuck a little bit and I only manage 1 or even 0, and sometimes I go a bit sort of faster than I expected, and so it seems pointless to stop. So the next question in my list says the following. So yesterday I did a question that involved things that the questioner called automata, and the next question is another question about automata. So what do these ones do? And by the way, this is question number 27 out of the 60 questions I'm working through. 3 automata I, R, and S. Let's put a little thing to say. What do? They print, again, pairs of positive integers on tickets. So this is what we had I did it yesterday, so on the previous video. And for every entry x, y, how x and y can be an entry is not yet clear. The automata IRS has input, then that was the most likely interpretation. Give x minus y, y, x plus y, y. So we had to add or subtract a multiple of y, and yx, respectively, as outputs. Maybe this time they swallow the input. Let's see if we can work that out. With these automata, well, actually, doesn't really make any difference, I think, whether we swallow it. Can I get the tickets A? Initially we have the ticket 1, 2. Sorry, I missed out that sentence by mistake, but that's the start. Can I get the tickets A 1979, B 819, 357. Find an invariant. I've got a bit of a guess here. I mean, I can already think of an invariant. What pairs PQ? I have a feeling this is just very straightforward if you know the right bit of maths. Can I get starting with AB? Via which pair should I best go? I'm not sure I understand that last question, but we'll think about that in a minute. Perhaps I do understand it, actually. Well, why I think it's easy is that the first 2 allow me to add an arbitrary multiple of y, whether negative or positive, to x. So I can do x, y goes to x plus my, y. But I can also, by commuting with this yx operation, conjugating with yx, I can also do xy goes to x, y plus mx. So if I want to do that, I just, I want to stick with xy. So I take my xy, I swap it over to yx, then I do this operation, and I'll get y plus mx x, and then I swap them around again. So that means I can do Euclid's algorithm. If I've got xy, I can just apply Euclid's algorithm until I get down to the highest common factor of x and y in both places, or even, yes, it prints pairs of positive integers, so I can get down to HCFXY, HCFXY. So the invariant is the highest common factor. It's easy to check if you aren't familiar with this, that the highest common factor is preserved. Can I get 1979? If I start with 1, 2, well, the highest common factor here is 1. So is the highest common factor of 19 and 79 1? Yes, because 79 is not a multiple of the prime number 19. I presume that these two numbers, this is a multiple of 3, this is a multiple of 3, so we can't get 819 and 357. What pairs can I get? I claim I can get anything starting with A, B, and the reason is that if I've got, anything that where the two numbers are have the same highest common factor. And the reason is if I'm supposing A and B, so this is, I'm still representing as a pair of numbers, so I'll put HCF, supposing HCF of AB equals HCF of CD, then I just do Euclid's algorithm until I get down to, and let's call it, I suppose that's a number R. I can get down to RR, and I can do Euclid's algorithm here and get down to RR. But these operations here are all reversible. So if I want to get from AB to CD, I just go down to RR and then back up to HCF CD. So via which pair should I best go? The answer clearly intended is RR. So that question was a sort of slight non-question because I could recognize Euclid's algorithm straight away. So I've taught it several times and that kind of thing. So that was just a little bit of experience, made that question easy. And I will now move on to question 28. N numbers are written on a blackboard. In one step, you may erase any two of the numbers. Maybe this will be my first chance to try to be properly systematic. Say A and B. And write instead A plus B over 4. Goodness. I'm punctuating it exactly as in the question. Repeating this step n minus 1 times. There is one number left. I think that one we can all agree on. Prove that initially if there were n ones on the board, again, I'm writing the question out exactly as it's written in the book. I would not usually use the full word when I'm referring to a number like that. At the end, I punctuate it slightly differently. A number which is not less than 1 over, okay. 1 over n will remain. Okay. Right. So my wish to be, I don't see straight away how to do this at all. But so what I planned to do when I was in this situation was to try to be systematic about it. And so the question I first have is, how could an invariant have anything to do with this? And secondly, what invariant might I be? I mean, what might the invariant be like? So I'd like to sort of try to narrow down the class of invariants I'll think about. And then even maybe sometimes you could sort of say, supposing you've got a particular category of invariant, then you can perhaps, maybe with a couple of parameters associated with each potential member of the category, you might be able to get some equations in those parameters or something like that. So that would be what I would consider to be a systematic approach. So I think I want an invariant of sequences A1 up to AN, and so probably going to be something like that, and I think I will probably want phi of just a singleton is likely to be just A, and then I'd like to prove that if I start with ones, then I'll end up with something that is at least 1 over n at the end of it. And how might I prove that? So one potential difficulty that I think I have is that, supposing I looked at something like 1, 1, and then very, very small numbers, sort of A3 up to AN, that are very, very close to 0, then it looks as though I can make any sort of invariant like the sum go down quite a lot. So the sum here is approximately 2. If I apply this operation, then the sum, if I want to make the sum go down as much as possible, then I'll add these two, because they're averages. They will then be, each one of these will be replaced by a half, so then it'll go down to half. So the sum of the AIs is going to go down by 2, a factor 2, but that assumed that these things were extremely small. But these things being extremely small is not necessarily going to be very easy to achieve after a few steps of this algorithm. And one small comment is that it feels as though we might be able to prove this not using invariance by some sort of inductive argument. But I think I'm going to, because when you've applied this algorithm a few times, when you started with 1, 1, 1, 1, 1, we could say that each number, so it's, after a few points we get A1 up to AK. Now each number here was built out of 2 numbers the stage before, and we can trace the ancestry, so to speak, of the numbers here. And we'll get some disjoint ancestries. That's a bit confusing to call this A. So we had some 1s up here. So this A1 is going to come from some of these 1s, and this AK and so on is going to come from some of these 1s. So the number of 1s that this comes from, if it's, say, R1 and this is up to RK, then if we believe this, if we believe the question, then we get that A1 is at least 1 over R1 and AK is at least 1 over RK. And so actually we can maybe say something. So if we've got the R1 plus up to RK equals N, and the numbers 1 over R1 up to 1 over RK seem to be quite significant. Just wondering whether something like the harmonic mean is going to be an invariant. What is the harmonic mean to start with? So just the harmonic mean in general. I'm a little bit shaky on all this. So the harmonic mean of A1 up to AN is 1 over A1 plus 1 over AN. So when you start, that's going to be, if these AIs are all 1, it's going to be 1 over N, which is highly promising. Maybe we can show that the harmonic mean doesn't go down. So let me just see whether that works. So for that I need that 1 over A1 plus 1 over AN doesn't go up. This is just seeing whether my guess is true. And when I do an operation, so then if I do an operation, say to A1 and A2, that'll replace them by, if I start with A and B, then the contribution to this, to this harmonic mean, it starts off as 1 over A plus 1 over B, but when I've done the operation, I've converted them into A plus B over 4, so I end up with 4 over A plus B. So I want 4 over A plus B to be less than or equal to, which doesn't look very promising, 1 over A plus 1 over B. Let's just, it's a slightly unpleasant inequality. 4 less than or equal to A plus B over A, so that's 1 plus B over A plus 1 plus A over B, so we want 2 less than or equal to B over A plus A over B. I'm now starting to feel happy, I think. So 2AB less than or equal to B squared plus A squared, and that is a true inequality because the difference is B minus A all squared. So I think what happened there? I had what looked like a bit of a flash of inspiration, but that's because I just had a little bit to think of what was going on, and the reciprocals became relevant looking. And so the harmonic mean naturally suggested itself, although it's absolutely not something I would just normally think of. So that's gone reasonably quickly. And I'd better move on to the next question, because I've got time for one more, I think. 29. The following operation is performed with a non-convex, non-convex, I'm getting slightly scared already, non-self-intersecting polygon P. Let AB be two non-neighbouring vertices. Suppose P lies on the same side of AB. I take it that means all of P lies on the same side of AB. Reflect one part of the polygon connecting A. Oh, goodness me, right, so it can take a little while to understand what's going on. Reflect one part of the polygon connecting A with B. At the midpoint O of AB. Prove that the polygon becomes convex after finitely many. Ooh, that's nice. I haven't understood the question yet, but I like the conclusion. Becomes convex after finitely many such reflections. Right, I absolutely don't understand what's going on, so let's try to think about it. Are there two non-neighbouring vertices? That's clearly important. Okay. So I think this is what's going on. So we have a polygon and here's A, so it's non-convex. I've drawn take a little hole out of it. And here's B, so they're not neighbouring vertices. So we draw the line here, and then the midpoint is O, and I've drawn this in a silly way because I now can't reflect this polygon. But reflecting, so the part connecting A and B is this part here, and when it says reflect the part at the midpoint, I take it that actually means rotate it about the midpoint through 180 degrees, so that we end up instead with something like that. And so we then get rid of this part, and this is our new polygon, which is still not convex, but then we can sort of put a line there and add that section on and add that section on, and so on and so forth. And we want to prove that eventually all the angles drop down below 180. And how do we prove that? I don't see an argument straight away. So now let me, again, in my attempt to be systematic, we know that an invariant is going to be involved. I would guess that, so the number of edges is going to remain constant. So it's going to be a polygon of the same type. If it starts off as a heptagon, it will always be a heptagon. That's an invariant, but not the invariant I'm looking for. That's just an obvious remark. So I think it's going to have to be something to do with the angles. The lengths of the edges are not going to change either. So it's something to do with the angles. We know that the sum of the angles is going to be another invariant, so that's not much use to us. because it's an invariant whether or not it's convex. We want something out of the angles that will probably just something that will increase every step or decrease every step that we take of this kind. So what happens when I do a step like this to the angles? So I've got let's just isolate the part of the picture that so far I think it can't be some linear function of the angles, so I think I might need to have some polynomial function of the angles. So that's just a thought I have in my mind at the moment. But let's say that this angle is alpha, this angle is beta, this angle is gamma, and this angle here is delta. Just for consistency, I'll put it. Then after this rotation thing, that's going to be parallel to this. This will be parallel to this, and this will be parallel to this. So we should be able to work out what these angles are. So that is, or should we? If I just increase this length, well, we know what two of the angles are anyway. We know that that one is pi minus beta, and that one is pi minus gamma. But do we know what those two are? So if I increase this length but keep that angle the same, I think that's going to, that's still going to be parallel to this. So, but this angle here will change, and therefore I can't determine what I care about is what this angle is. So that, I think I can get what this angle is because I've got this being paralleled. The angle from between here and here I've got this direction and I've got this direction. Okay, so let's just try to write something in. So I've got pi minus beta there, I'll put that in, and pi minus gamma here. I know that those two, I know what their sum is going to be. And I'm fairly sure I ought to be able to work it out, but just before I go into that slightly annoying process of seeing whether I really can work that out, I want to just think about what the invariant might possibly look like, what seems to be going down. So we seem to have some really quite sharp angles here, which have gone down to some flatter looking angles. So we gained some convex bits, some bits where the angles were smaller than pi, but we lost, so here we had an alpha which is now become concave rather than convex, so to speak. So could it be actually that if we just sum the sort of the negativity, so to speak, so the negativity here would be I add this angle, and then the negativity here I add this angle and this angle. It looks as though it goes, actually it's sort of maybe more natural to add pi minus this angle to pi minus this angle, because that's somehow what makes it negative, or maybe even beta minus. Yeah, anyway, I'm sorry, I'm just worrying about what the sign of my invariant might be. Let's not worry about that. Let's just add the angles. And so here, I've got two angles, and then here I've got what looks like two bigger angles. And in general, maybe I can just think about what happens. So in general, I've got something like this. So I've sort of guessed an invariant. I think maybe polynomials was a bit too complicated for a question like this. So I have an angle here, and then something funny happens, and I have an angle here. So this could be wildly non-convex, and I'm not going to think about that. And the reason I'm not, hold on. Now, why was I not going to think about that? Because actually each angle that was bad, so to speak, down here became good, but also there were angles that were good that became bad. So I have to be a little bit careful there. But perhaps if I were to say the following, supposing I just draw that and call this angle here theta, then I know all about the sum. So that's pi minus alpha, that's pi minus beta. Then I'm going to be able to say what the sum of these angles is, and in particular I'll be able to say what the sum of the negative contributions minus the sum of the positive contributions is, and then I have to think about what happens afterwards. So afterwards, I'll come back to that in a moment. This is draw. I then add in this, and I add in this, and then I add in something funny here. So supposing I've got k edges, I have to remind myself what the formula is for the sum of the angles of a k-gon. So for a triangle it's pi, for a square it's 2 pi, and so for a k-gon it's k minus 2 pi. So the sum of the angles, just looking downwards here, not including these two, is going to be k over 2 pi minus theta minus pi over 2 minus alpha, minus pi minus alpha minus pi minus beta equals k minus 4 pi plus alpha plus beta minus theta. Now what is that? That was the sum of the angles looking in that way. it's a k-gon, so how many of those angles are there? There are k minus 3 angles. Add to this thing here. So if I look at, so now if I look from downstairs, so I'm looking at the equivalent of this beta and this gamma here. I'm still ignoring this alpha and this beta. So the angles from below, so I've replaced each one by pi minus itself. So they add up to, sorry, k minus 3 angles from below add up to k minus 3 pi minus this lot here. So so that gives us pi minus alpha minus beta plus theta. That looks slightly wrong. Oh, sorry, it should have been 360. Oh, sorry, 2 pi minus, not pi minus. So I get 2k minus 3 minus, I write it, 2k minus 3 minus k minus 4 equals k minus 6 plus 4, so k minus 2, just check, minus 6 plus 4, yes, minus 2. So I get k minus 2 pi minus alpha minus beta plus theta. And so the negative contribution so sum of what can I say about the sum of the angles that are greater than pi? I feel it looks as though I can't say anything very much. So maybe I'm barking up the wrong tree here. Well, I know what happens to the sum of the angles greater than pi plus the sum of the angles less than pi. But that is not relevant. I've just heard noise from outside this room. There's going to be a bit of a noise. Ah. There we go. So I think I'm going to, this was looking at things quite generally. I may have had some useful ideas there, but I still feel I don't quite know what's going on. I want something to go down when I do this process. How do I systematically find an invariant that will do the job? So here, and then here. Could it be that what happens to the number of angles that are greater than 180? That would be much nicer than actually having to work out what all the angles are. So here I had 2 angles that were greater than 180, but after reflecting, or whatever you want to call it, unfortunately I still had two angles that were greater than 180. But something seems to be going on. So actually one little remark which now starts to feel helpful. Sorry, I've just had a sort of had a little thought that has just jumped out at me, which is I have a horrible feeling that this is just a question of looking at the area of the polygon. So I was going down absolutely, if this works, I went down completely the wrong track thinking about the angles. So why did that idea occur to me? I was sort of somehow thinking that when I did this, it was sort of irreversible. I can't get these. So at the first step, I arrived at this outer polygon here, but there's no way I was going to sort of reconvert these things back down to where they were before. On the other hand, it doesn't mean they can't ever become 100 greater than 180. I think in some cases they could, not in the way not in the drawing I've got here. But then it just sort of something seemed to be. I had this sort of feeling that about unfolding the polygon, it was going to have to stop at some point, and then I realized, of course, that is the case. And so the area goes up at each stage. The area is obviously bounded in terms of the, the sum of the lengths of the, or in terms of the lengths of the edges. We could easily get some upper bound. It's quite amusing to think about what the best one might be, but we don't have to do that. And so the only thing that's left to prove is that there are only finitely many possible areas that you could have, given that you've done this unfolding operation to your starting polygon. And that should be straightforward, but I don't straight away see it. So I'm now just all I'm looking for now is a quick proof. And if you start with some bizarrely non-convex polygon and you do this unfolding, so maybe start here or something, then there are only finitely many polygons you could ever draw. So or another approach would be to say that the area goes up by at least some particular amount at each step. So that would be enough to show that the process has to terminate. So is it simple to see that there's some lower bound for the amount that the area could ever go up? I think we've got the angles, so the angles will generate. No, this doesn't work if I've got some irrational relations between the angles. So what I was thinking about was that maybe all the angles you ever get are somehow related in some nice arithmetical way to the angles you started with. So if you've got an angle that's incredibly close to pi, and then you do this reflection operation, you increase the area by a very, very small amount. So it's not absolutely clear. So why can't we just keep on and on increasing the area by an absolutely tiny amount, and sort of somehow generating by this process of changing angles, generating new ever smaller and smaller angles, because the ratios of the original angle were not rational. If the ratios were rational, then I think it would be possible to prove that there was some smallest angle you could possibly ever, or nearest to pi angle you could ever possibly make. But we don't seem to have that here. But I do feel that there should be some way of doing this. So I'm still pondering this question: how can we prove that the process terminates in a finite number of steps? Is there by any chance something else that's going down or going up? I thought the area was really quite a nice idea. Or another possibility, actually, perhaps we could think about the number of vertices that belong strictly inside the convex hull of the polygon. That might be something that goes down at each step, and that would be even easier than the area. So let's just draw something. So I've got this, I've got that line, which is meant to be a dotted line actually, and then I've got a bunch of stuff and I don't know what's going on, and then I've got the rest of the polygon and I don't know what's going on there either. So I'm just going to draw it as a curve. Now I take its convex hull, that's the smallest convex polygon, or convex shape, which will be a polygon, but, so I'm not drawing this very well, it contains it. Now after I've done this operation, I had some vertices here that were inside the convex hull, but after I've done the reflection, those vertices jump outside the convex hull, not all of them. They all jump out of the convex hull of the original polygon, but not necessarily out of the convex hull of the polygon that we've now ended up with. A slight problem there is that these two vertices could now belong to the convex hull, but let's just, in fact, quite a few vertices might be able to. So that doesn't seem to work actually. I think I've got a counterexample. Supposing I have lots of vertices all along here, then I've got a point there, then it goes right down like that, and then I've got lots of vertices, and that goes there, and then it just goes around like this. And if this gets reflected right up to here, then the convex hull suddenly contains a whole bunch of vertices that it didn't contain before, when the ones that have come out, I've only sort of brought two vertices out, but put a whole large number of vertices in. So that didn't work. So actually the area seems more promising after all. So let me go back to thinking about, unless there's some modification of this number of points in the convex hull idea. So what can we say about what happens to the area when we reflect at a particular vertex, or in particular two vertices? It's going to go up by at least what? I feel there should be some really simple reason that the process has to terminate, but then that simple reason feels as though it would be yet another invariant. So I wonder whether I can draw a whole bunch of things that would be connected with the original polygon and say that the area must be built out of those in some way. So I'm going to think about an example here. So roughly the same example I've been thinking about up to now. So we have something that looks a bit like this. So then we go up to here. And then the second time, we've got this triangle here that is going to be the thing that's reflected. Now, what is that triangle in terms of the original shape? It's made out of replacing this by this. So I could actually make it much flatter, and I think that might be more sort of instructive. So if I did this, then when I reflect, I get that, which is a much, much flatter triangle than the one I started. But, okay, I think I might finally have got there. So this edge is going to be parallel to this edge. And so if this edge is actually parallel to this completely, then I'm not going to do the reflection. So the amount by which I'm going to reflect this triangle, also the amount of area I add, is going to be some function of, well, the height of this triangle, which will depend on this angle here and these lengths. You know, if these lengths are reasonably large, and we know what this angle is, and it's not exactly 180, and we get some lower bound on this area. So maybe what I can say is that if I've got a lower bound on all the lengths of the edges of the polygon, and I've got a lower bound on the differences of the angles between the edges, differences of the directions. So when I take A to B, so it comes in like this and goes out like this. There's a sort of, these two edges can't be two different. Actually, I don't care about those ones. What I care about is the area here. So if it entirely lies inside this very, very close this very small region here, just below the line, then that's going to be, because the lengths are bounded below of the edges, somewhere along the line there's going to have to be, even if it did something zigzaggy like that, there's going to have to be an angle that's either very, very close to 0, or very, very close to pi, because the edges are not super short, so we can't do something like that, keeping all the angles sensible. So I'm saying if I make this close enough to this, then given that the edges are not massively short, then they're all going to have to go almost horizontally in that direction, or almost horizontally in that direction. So we're going to get some angles that are extremely close to naught or to pi. And therefore, since I think we can say there will be a lower bound on how close they can be to naught or pi, and we've got the length, then I think that's going to give us a contradiction, and therefore that there must be a point that's a bit further out from this line, which gives us, I think, a lower bound on the area that we add when we do this reflection. Although, why does it give us a lower bound on the area? If I've got just one point here, it could go almost horizontally. Oh no. Yes, no, almost horizontally, and then the next one. Oh, right, no, I think my reasoning is that the next one is not going to be allowed to be too close in direction to the first one. And so we'll get at least this amount of area. Yeah, I think I'm going to stop there, because I think writing properly what I'm trying to say here would be a bit nasty, but I think I have got the sort of bare bones of a proof that the amount of area you add at each stage is bounded below in terms of the original polygon. So that was an interesting one, actually, because I was going down completely the wrong lines and then suddenly it popped out. And again, quite why that happened, I don't know. I think unfortunately, I think it might have been just by visualizing, so sort of feeling as though something was sort of increasing in a way that it couldn't carry on forever, and then, oh yes, of course, we're just adding to the area.